Write down 15. Write down determination of velocity of sound and end correction using a closed resonance tube and a set of tuning forks right? Within brackets, write to the title or below, same setup. So there's no difference, right? Setup is the same, you use that, setup is the same, right? So if the setup is the same, but here we use only the fundamental wave pattern. We use only the fundamental wave pattern, right? This wave pattern. So we have E, then L. So for this one, you can write, there's a fork. So we are going to use different forks, right? About 6 forks. So here, lambda over 4, this is lambda over 4 wave pattern, is equal to L plus E. Then lambda is equal to 4 times L plus E, right? Then you are going to apply this equation, V equals F lambda, to this form, for the fundamental form, right? Right, draw this one and write these equations, and thumbs up once you're done. So this is 15th experiment, right? Sharu, 15th experiment, take this down, right? Okay. So here we are using a set of tuning forks, right? So if you are using a set of tuning forks, what we are changing is the frequency. So you are using different tuning forks, then you are changing the frequency of the tuning fork. I mean, not the frequency. You are using different frequencies of forks. So you know that if we apply V equals F lambda, this is for the fundamental, right? We are only using this for the fundamental. We are not using other resonances. We are only using fundamental. So you can apply V equals F lambda. So V is equal to frequency. Lambda means this, 4 times L plus E. So here, what we change is the frequency. Frequency means frequency of forks. We are using different forks, means we are changing this frequency. So this is independent variable, right? Or X. This is, you can use that as independent variable. So when you change F, velocity does not change, right? When you change F, that depends on frequency's length. So when you are having higher frequencies, this length becomes less. When frequency of forks increases, this length becomes less, right? So this L is related to Y. Y is dependent variable. So you have to subject L, right? So when you subject L, you can write V of 4F equals L plus E. So L is equal to V over 4F minus E. Like that, you have to subject L. We are forming this into a Y equals mx plus C. Then just change the sides. So L is equal to V divided by 4 1 over f minus e. So this L is y. V over 4 is gradient, right? M. 1 over f is x. Then by the intercept, you can find the n correction. So that is it, right? So the gradient, so before that, before finding the gradient, you need to draw the graph, right? So for the graph, what do we need? We need to get a table. L values and f values. So what do? You usually start from the highest frequency fork. So for the highest frequency fork, you will have the least resonance length, right? For the highest frequency, you will have the least length because these are inversely proportional, right? So you start the experiment, no, not starting the experiment. You will start taking measurements from the highest frequency fork and in the descending order. So you will have lowest length, right? So you get a highest frequency fork. So for that, you place a fork, then for that check the resonance while lifting this. Then you can measure this length. Then you put that value here. Likewise, for about 6 tuning forks, you get resonance lengths. Using this, you get 6 resonance lengths about, right? So once you get these x and y coordinates, actually x coordinate is 1 over f, right? So once you know this f value, you can calculate 1 over f. So this is x and this is y. So those are x and y. Now you know x and y, 6 x and y coordinates in order to draw the graph. So if you get the shape like this, so the graph should have a positive gradient, right? This is a positive gradient and a negative intercept. So negative intercept like that and positive gradient. Graph would be like this. For the y-axis it is L, for the x-axis it is 1 over f. So once you draw this graph, you mark this coordinates, 6 coordinates and draw the graph, right? Base fitted line. Then if you get a graph like this, these results doesn't have a considerable error, right? Then from this graph, you can find the gradient. So that gradient is equal to what? V over 4. So the gradient you know, then V is equal to 4m. 4 times gradient. Then magnitude of the intercept. This is E, right? E is equal to, n correction is equal to magnitude of intercept. Okay. First take this down, then take table. From the table you draw the graph. From the graph you calculate V and n correction. So this is a more accurate method, right? Because the random error is less now compared to the previous method, right? For the previous one you used a one fork and didn't use a graphical method. So there are random errors, right? So for this one, since you are using a graphical method, in order to find V and E, same thing, right? But for this V and E, the random error is minimized because you used a graphical method. So that's the only reason. Okay, take this down in order, right? Here, table, graph, then you find the values. That's the order. Take this down and thumbs up. Okay. Draw a line to this one, then write before taking measurements, get the lowest frequency fork, get the lowest frequency fork to check whether the length of tube, the length of tube is enough, is enough if it is not enough, another sentence, if it is not enough, the tube is to be replaced, the tube is to be replaced by a lengthier tube, is to be replaced by a lengthier tube. Okay, so you get the lowest frequency fork, right? So if the frequency is lowest, L is largest, right? So if for the lowest frequency fork, lowest frequency means largest fork, right? Remember I discussed that set of tuning forks at the last class. Lowest frequency fork means largest fork, right? You get the largest fork, meaning lowest frequency fork. Then the resonating length is highest for that. So for other forks, L will be lower values, right? If for the lowest frequency L is sufficient, for other forks also L is going to be sufficient, right? Because L will be less, resonating length will be less for higher frequencies. Understood? So that is what it means. So first you have to make sure that this resonating, the tube is, length of the tube is enough to get the resonating length, this length, right? You don't mark these two values when you are drawing the graph. First you have to make sure that it is enough. After that you start taking measurements. Then those measurements will be filled in this table, right? Then what do? Then you start taking measurements. Then you start, so you start from the lowest frequency before the experiment, right? When taking measurements, you start from the highest frequency, right? Highest frequency means lowest lengths, right? So this is done in order to get, you have to make sure all the values in all the time. This is for the fundamental, right? I discussed that at the previous one as well, last class as well. You start from the largest fork, right? Not largest fork, highest frequency fork. You start taking measurements, right? Write down this below that. We have to make sure all the resonances are at the fundamental, within brackets write same procedure of 12 and 13. For this, next line, for this, measuring should be started from the highest frequency fork, from the highest frequency fork, and continue in the descending order of frequencies, the descending order of frequencies. Other facts, next point, right? Other facts are discussed, other facts are discussed at the 14th experiment, at the 14th experiment. So we discussed all the 6 experiments in depth, right, of waves and oscillations. So you can understand that as we are discussing earlier experiments, those experiments are linked, right? The more you do, the less difficult it gets, right? The more you do, easier it gets to study this, because there are common things as you are discussing these experiments, right? That's the thing about that. We'll do a question. Take the PDF I sent you earlier. That is the first question, right? I think you have that in the group. I'll resend that. Okay, I sent the PDF. Try the first question. That is 1991, right? 1991 question. So an experimental setup used in the laboratory to determine the speed of sound in air by resonating air columns is shown in the figure. Briefly describe the procedure that you would adopt to obtain the fundamental note of vibration of the air column with this setup, right? So you need to gain the fundamental note of vibration, right? This shape. Here also you have so what is the procedure? You start from the lowest length, right? You start from the lowest length. You almost immerse the tube, then you lift it up gradually while sounding the fork, right? So when you hear the resonance for the first time, that is the fundamental wave, right? That is the fundamental wave. Write down. You can write this in on your own words as well. You should be able to write this, right? You have to have the practice for that as well. Write down starting from a small tube length, gradually increase the length of tube while sounding tuning fork. While sounding tuning fork. When the sharp sound is heard for the first time, the fundamental, it is when the fundamental resonance length, So you have to practice writing these answers, right? In sentences, you have to be able to write what you mean actually, right? You have to correctly write that and in full description, right? You have to give a full description and it should be short. You don't have to make it like lengthier, but you have to mention all the important parts there, right? You have to practice that. You can first write the answers, then try to, check the answers in the market schemes. Then you will get into the pattern of those answers, right? That's why writing these past paper questions is important, right? then you can understand what they hope that you have understood. Okay, right, then simple B. If the corresponding length of air column measured in A is L and the wavelength of sound wave in air is lambda, write down the relation between L and lambda. So easy, right? So you know that lambda over 4 is equal to L. You can write this, or you can write L equals, doesn't matter. Okay. For the fundamental, it is lambda over 4. Okay. Lambda over 4 is equal to length, resonating length. Don't put n correction and all those stuff, right? Because they haven't mentioned that n correction in the question. You don't have to do unnecessary things. You exactly have to follow what they mean by the question, right? You have to follow those steps exactly. Don't write other stuff, right? So they are only asking about simple L and lambda. So you just write this down. Okay, part C. Rewrite the expression in B in terms of L, speed of sound V, and the frequencies N of the tuning fork. So they are asking you to put V equals F lambda, right? But here V, you can take it as V. For the frequency, they say it is N, right? So use N, don't put F there. So for the lambda, you can write 4L. So this is what they ask. Don't write other stuff, right? You have to follow exactly what they say. V equals 4NL. Then second part. If you are provided with several tuning forks of known frequencies and asked to determine V by plotting a graph, state the quantities that you would plot independent variables. So independent and dependent, you should be able to identify those two. So here what we change is the frequency, right? Frequency of forks. Actually we are changing the forks, thus the frequency changes. So what we change is the X. What we change is X, right? X means independent variable. It does not depend on anything. It is independent variable. So first you have to form this in order of y equals mx. You don't get a intercept here because there's no n correction. So n is related to x. Doesn't mean equal to x. It is related to x. It is what we change. It could be 1 over n, n squared. It depends on the equation. X. All we know is that n means the frequency, is what we change. Then depending on that, y changes. This is the dependent variable. So you have to subject dependent variable. So if you subject that, v over 4, n is below. So this is y. 1 over n is x. So you have to show that independent variable is what? Not n, right? If you write n, they won't give you marks. Independent variable is 1 over n is equal to 1 over n. Here what I mean is that this is related to independent variable, but the independent variable actually is 1 over n. Then the dependent variable is obviously L. Then the gradient is V over 4. Okay, with a certain tuning fork, the value of L was observed to be 35 centimeters. 35 centimeters. If the length of the tube is 75 centimeters, right? So the length of the tube is 75 centimeters. Resonance length, the length that this value. So at the fundamental length is, they say 35 centimeters. At the fundamental it is 35 centimeters. So what they ask is, is this enough? You are using the same fork. If this tube is enough to have the another resonance length. So that's what they ask. So what's the thing? Another resonance length is like this, right? In order to make this wave pattern, so here you only need lambda over 4 length. You need here 3 lambda over 4s. Okay? Lambda over 4, lambda over 4, lambda over 4. So you need 3 lambda over 4 length. So lambda over 4 length is 35 centimeters. What is 3 lambda over 4? It is 35 times 3. 15, 10, 105 centimeters. So it is not enough, right? So 75 centimeters is not enough. In order to make the another resonance length is 105 centimeters. So obviously it is not enough. Right? You don't have to write these stuff. If you want for the clarification, you can write. But for the answer, you can simply do this calculation and explain, right? You can write like this. You can find next resonance length equals 35 times 3, 105 centimeters. You can write that. So the next resonance length is 105 centimeters. Then you can write, therefore, it is not possible to gain the next resonance length with this tube. If the room temperature increase, would you expect L to be greater than, equal to, or less than 35 centimeters? So if the room temperature is increased, V increases, right? Remember, gamma RT divided by capital M. So if V increases, L increases. You have to expect a larger resonance length, slightly larger, right? So you have to write, you have to first write, it will be more, right? Then they are asking for the reasons, then write for the reasons. Don't just write only for the reasons, right? First you have to mention that it will be more than 35 centimeters. After that, write reasons, right? Otherwise you would lose 1 mark for the first question there. Okay? So just you have to write L will be more than 35 centimeters first. Then write the reason. What is the reason? When temperature increases, velocity of sound increases. When velocity of sound increases, L increases. If you want, you can write this equation as well there. Then the next part, simple F. If alcohol is used instead of water in this experiment, would you expect the same value for methods in C? So for that one, you have to first put no, right? If you put alcohol, it changes capital M. Remember, it changes capital M. So no, right? Then they ask the reason. Explain your answer. So what's the answer? The alcohol evaporates easily at the room temperature, changing the composition of air inside the pipe, right? You can write this in your own words, but you have to mention those certain facts, right? So what's the thing? Alcohol easily evaporates at room temperature, causing the composition area of inside the pipe to change. Then simple G. For accurate calculations, an end correction has to be introduced only to the open end for the tube and not to the closed end. So what they say is it is obvious, right? So here you have the closed end, here you have the open end. End correction only happens at the open end, right? At the close end, there's no end correction. Because here it is open to air, so this wave pattern deviates outside the pipe. Write down, in the open end, air is exposed to the outside. Therefore, we cannot confirm the maximum displacement of partial occur at the corner of the tube. At the closed end, it will be an antinode, so the particles does not move. Right? So at the home, try these questions. 1991 we did, right? 2002, 2003, take this down, 2003, 2011, 2013, 2016.